All right, thank you. I'm Michael Martin. I'm a current Science and Technology Policy Fellow within the Office of Advanced Scientific Computing Research, and I will be moderating this session. So our first speaker will be Andrew Stershik, who is completing his PhD in Civil Engineering and Computational Mechanics at Duke University with John Dolbal as his advisor. He completed his practicum at Oak Ridge National Laboratory, and this actually marks a bit of a homecoming for him because he's a graduate of the University of Maryland right up the road, where he completed a double degree in Civil and Environmental Engineering and Economics and was awarded the Outstanding Senior Award within Civil Engineering. Andrew?
Thank you. So the title of my talk today is the application of numerical methods to study arrangement and fracture of lithium-ion microstructure. And this isn't a typical civil engineering topic, one might say, but I kind of tied in with fracture mechanics, and that's really computational mechanics is our department's specialty. So the motivation for my project is really in the field of energy storage. And so if we look at this image here on the left, we have a cell phone with the battery taken out and it's been smashed apart. And so really looking at both the battery, the energy storage problem, and both the fracture problems that you can see on the screen of the phone. Energy storage is an increasing societal question. We'd like to see efficient energy storage for our consumer devices, but also as we're looking at more into hybrid and electric vehicles, we need efficient solutions for vehicles, as well as the possibility for using batteries as energy storage techniques for grid scale power. So on the left here or in the center is a plot of the output of a solar farm in Arizona throughout the course of a day. And you can see it's generally the sinusoidal shape, but as every cloud passes over, there's a high degree of variability. And coupling this solar farm with a bank of batteries can greatly smooth the output and ease the load on the grid. And of course, here on the right is a well-known image of a Tesla car with a battery fire. And this simply shows that there's still an opportunity to improve the safety of these energy storage devices. Just a quick diagram of how these batteries look inside. There are two sides, the anode and the cathode. And as the battery charges and discharges, lithium ions are traded between the two sides. And electrons are transferred back through the current collectors to the application or the power source. And I'll be looking in my research a little bit more into the microstructure here within the cathode. Specifically, I've been looking at the compaction of the electrode material during manufacturing. So on the left here, we have an image of these active material particles, which in this case are nickel, manganese, cobalt oxide. And these absorb and release the lithium ions as the battery charges and discharges. Through the course of manufacturing, these active particles are deposited in a slurry onto a plate and then pressed to be a much denser assembly, something like this. And during this compaction process, using X-ray tomography imagery, we can see that before compaction, some of these active material particles have some voids or flaws in the centers of them. And after compaction, many of these larger particles especially have split apart. The impact of this particle fracture, it can change the electrical properties of the battery. As the contact network between all these particles serves as a pathway for electronic transport, thermal transport, and mechanical forcing, it's important to develop an approximation for this contact network and then see perhaps how fracture might affect contact pathways. In one of my first studies was to looking at this contact network, and so we employed the fabric tensor, which is a mathematical construct, as a directional measure of this contact distribution. So beginning with the raw data here, which is X-ray tomography of battery cathodes, we developed several geometric approximations to determine the actual contact pathways within this assembly in the cathode. And we also used a common numerical model called the discrete element method over here, in which we approximate all these active material particles as spheres, compress them, and compare that to the reality. And the simulation would look like this. Compress it down. And so in doing this, this really simulates the the manufacturing process wherein the power density is greatly increased by putting these particles through a roller and smashing them down. We use fabric tensors to compare the contact distributions before and after this compaction. And so what a fabric tensor is simply a tensor approximation of a directional data set. So we can think of a scalar approximation. The most basic one might be an average. And this is simply increasing orders of magnitude, or increasing orders of approximation, and in a directional sense. So if we have a true distribution of two-dimensional vectors that might look something like this, we can approximate them in a second order manner by this fabric tensor, and in a fourth order by this. And again, we can do the same thing in 3D. And really, this just helps us get a sense of before and after compaction, how can you characterize this distribution of contacts, and perhaps how do they change in between. So here is just some sample fabric tensors from the battery cathode. Here is the tensor at 0 bars before compaction, and we can see that this kind of peanut shape here is rather vertical, meaning a lot of the contacts between the particles are vertical and relatively few are lateral. And after compaction becomes much more round, so the contacts are more uniform in all directions. Subtracting these two shapes can give you the change in the directional distribution through this compaction process. And here we can see with the blue colors being negative and the yellow to red being positive, how it relatively shifts from being more vertical to being more lateral than before. And we find that in doing this fabric tensor comparison, that all the different geometric approximations we've made to the cathode geometry, some spherical, ellipsoidal, or directly looking at the imagery, the fabric tensors capture this change very consistently. The only difference is that when using the DEM, it does not match nearly as well, and part of this is because it is missing the effect of this particle fracture. In that the DEM model, we have these unbreakable spheres as the active material particles, and they don't split apart during compression like an actual material would. So that's sort of certainly a weakness of a DEM model, and one I'd like to address eventually. And so going back to this image here, really looking again in the next step at being able to model the fracture of these active material particles, because it is a weakness of these spherical-based DEM models. And so looking at fracture models, one of the most commonly accepted fracture models right now in the world of finite elements is the cohesive element approach. So in this approach, we take our regular finite element mesh, and anywhere a crack may open, we insert zero-length cohesive elements between them. And the opening of a crack is governed by what is called the cohesive law of these cohesive elements. So that inserts a certain toughness which corresponds to actual crack opening properties. The trouble with this cohesive element approach is that it's highly mesh dependent. And so if we have an example here on the right, if the ideal crack path is this straight line here on the left, the best representation by a cohesive element approach would be this zigzaggy line here. And no matter how much you refine this mesh, this zigzaggy line will always be longer. And in this particular case, I think it'll always be about 8% longer. So this really is a problem in that cracks of the same length dissipate more energy, or cracks that in the simulation dissipate the same energy are shorter and are not on the exact correct path. There have been some techniques to address this problem, like the extended finite element method. You can see here this allows for arbitrary cuts through these elements, but the representation for three-dimensional problems can be quite difficult. So part of my work has been using this new numerical model called the thick level set method. And this is a non-local damage model which incorporates a characteristic length to limit the damage gradient. It uses level set based crack identification, and damage evolution is controlled by averaged quantities. And looking at this diagram here, in the bulk, it's mostly an undamaged domain, but there are several spots of damage. Here we have an area where this damage indicator function is greater than the characteristic length, so damage equals 1. And it's separated from the undamaged zone by this characteristic length LC. And using this damage evolution by averaged quantities within this damaged band of a certain thickness addresses some of the issues of other numerical models. And using the level set basis for this damage indicator allows us to have this technique be mesh independent and allow for arbitrary crack geometries. Additionally, just numerically, the way this works out, we've constructed the TLS model so that we do the update of each damage zone individually, and so there's no global solve over the entire domain. So it's quite a bit more efficient than other leading models right now. Looking at the thick level set model for a one-dimensional fragmentation problem, so say we have a brittle domain here, it's fixed on the left and pulled at the right, and we pull it faster and faster. We might expect some flaws would open. And from these flaws, we have release waves. And depending on the speed of these release waves compared to the speed of the opening, we might get a different number of fragments. And so if the loading is very fast, we'll have very many fragments. If it's slow, we'll have very few fragments. Running this study with our thick level set code, we have found that our numerical model matches this expectation very well as those of other numerical models. And it also matches fragment size predictions from actual fragmentation experiments. This model has also been used in 2D crack problems where we predict a crack path shown here in red, and that matches a experimental crack path shown in gray. And then my push has been in implementing this code for 3D problems to work up to the fracture of these battery cathode particles. So we have done a few simple test problems of plate tension where we see we have a plate pulled apart and we see that cracks develop as expected from the stress concentrations. We can do the same for plate shear, and we see a diagonal crack that grows. And just due to the high rate of loading, we see secondary cracks that grow as expected. And if we slow the loading, we get the quasi-static crack that we expect, which compares well, of course, to experimentally observed patterns. Moving into three-dimensional problems, we've been able to apply this model to the compression of 3D spheres. So say we have a geometry like this. By symmetry, we model only one octant of it. But as we compress the sphere, we note that a conical fragment results, and this matches extremely well with experimental evidence. And lastly, we've been able to apply this model to the 3D particles taken from the battery tomography, and taken here 2 sample particles. We can observe that the particles split in half due to the loads we apply. So in engineering significance, the fabric tensor analysis can be used to identify these transport pathways. Battery designers can use the new fracture model to effectively analyze particle failure due to manufacturing loads as well as other operational and exceptional loadings. And this model can also model fracture in many diverse fields of application. And I just wanted to also note the importance of parallel and high-performance computing in achieving this task, or achieving this result. In doing the DEM models for the cathode, these were really made tractable by running them on clusters. And if you were to do something like this, which is the simulation of a sand stack simply being compressed, it really would be impossible without using a supercomputer. And so I did have the opportunity to run this at Oak Ridge, and it's just an amazing opportunity. For the 1D fragmentation problems, I was able to distribute this on our cluster here at Duke and run 128 simultaneous simulations to greatly improve the simulation process speed. And then for our 3D fracture problems, the simulation was hastened by using parallel solve. And if you were to simulate many particles or the entire cathode, parallel computing would be absolutely critical. I'd like to thank the contributions of my co-authors, mentors, thesis committee at Duke, as well as at Oak Ridge National Lab and École Centrale de Nantes in France, as well as my peers at Duke, and funding, of course, from the Department of Energy. And with that, I'll take any questions you may have.